encoders and can.
Okay. All right. So let's start that.
Yeah.
Good. Yeah. So this week I'm going to cover the extension of autoencoders, which is variational autoencoders, and I'm going to do a brief introduction to GANs, which is Generative Adversarial Networks. So my name is Ali, and let's get started. So this is just an overview about what I'm going to talk about. So I will first talk about the basics, like I did for the autoencoder, and I'm also going to talk about the architecture, also a little bit, and then we will do a hands-on example. And if there is still time left, I'm going to do a brief introduction to generative adversarial networks. So let's go to basics regarding the autoencoders. And if you remember from the last week, autoencoders are mostly used for dimension reduction, and it is capable of extracting the latent space representation out of the data that you give or that you provide as an input. The problem with the autoencoders are the latent features are usually hidden within the weights of the layers. And the layers, the weights within those layers do not mean anything mathematically to humans. So we need something more explainable, and that is how variational autoencoder started to get a traction. So the purpose of variational autoencoder is when we want to use the autoencoders for data generation, the weights by themselves are not well defined enough, and they are not going to be able to create good data generation. But this does not directly apply to variational autoencoders. So if we wanted to compare autoencoders to variational autoencoders, as I said before, the latent attributes or latent features are usually hidden within the weights, whereas for variational autoencoders, the attributes can be represented as a distribution. So this is giving us a lot of versatility regarding the data generation. And which I'm going to talk about the next slides. But the caveat that you need to take from here is, again, the architecture in general is not different than autoencoders. The variational autoencoder has an encoder part and also a decoder part. The difference is the encoder part is generating the distribution over the latent features, and the decoder is decoding the encodings. Well, basically they are the distributions to get an output out of your network. Supposedly, this leads to less overfitting and more generalization of the data. This may seem an advantage for many applications, but for some niche applications, this is not an advantage, like less overfitting and more generalization. And specifically, if we are talking about anomaly detection, sometimes we don't want that. But that depends on the application. And because now we are holding every data, the latent features within the distributions rather than weights, which is basically some set of constant numbers. Now we can use the distributions to generate new data out of it. Because remember, if we have a distribution, we can pick new data from that distribution, statistically speaking. And one more thing to talk about is if we again compare the autoencoders and variational autoencoders. So if you remember from the last slide, we talk about the distributions. So the architecture also represents how we need to, like the picture on the right side, it also shows or illustrates how we need to introduce the distribution into our deep neural network. So because we are talking about the distributions, we have to have a set of neurons that is supposed to have mean value and the standard deviation. And we have a new layer that is creating samples from the given mean and standard deviations. So everything is going to collapse to something more valuable in the next slides, and actually with the hands-on experience, it will even make more sense. But for now, our purpose here is training this network to find mean values and standard deviations that is going to represent the latent distribution in its best ability. So suppose that because I'm trying to find the latent distribution Z, suppose that we call that like true latent distribution, where X is the input and Z is the output of the hidden variables. And this can be represented as probability of Z given X. The problem is this distribution is a posterior distribution and it is intractable. So an example to a similar case is, for example, when you say, I have a flu, the common symptoms are cold and nausea maybe. But if you go to a doctor and you say, hey, I have a cold and like my stomach is upset or something like that, then doctor needs to do new tests to pinpoint what your diagnosis is, because there are so many features that share the same common symptoms for the same sickness, for different sickness. So it is similar here. Generating this distribution is normally through like theoretical formulas. It is almost impossible. However, using the variational inference, which is what the variational autoencoder is providing through training, we can approximate to that posterior distribution. So then our purpose for this network is, the first task is, which is coming from the regular autoencoder. We want to minimize the reconstruction error between input and output. And as you remember, this can be a mean square error, or it can be a binary cross entropy. Or, the second task for the training this network is minimizing the distribution between the true latent distribution and the hypothetical distribution that we are trying to find. So that is usually called divergence. So we are trying to test how much the original, how much the latent distribution that we find is deviating from the original distribution. And usually people are using Kullback-Leibler divergence criteria. You can check what this does specifically, but this is not the only one that people are using. There are other divergence criteria that you can use. This is the most commonly used. It has some advantages and disadvantages when it comes to trying to generalize some problems. To sum up, what's happening here is we want to, for this network, we want to have a loss function that we are trying to minimize, and it is a combination of the reconstruction error, which is basically, again, the error between the input and output. And on top of it, we want to minimize the divergence error, which is the error between the true latent and the hypothetical latent distributions. So the paper that I referred at the end of the slides are explaining how you can derive a divergence criteria from the non-divergence criteria. You have to go through some set of rules. So I'm not going to go through that. Instead, I'm just going to go ahead and use already a settled one like the Kullback-Leibniz divergence criteria for implementing an example. So again, the purpose here is we have the MNIST data sets, then, and we are trying to reconstruct the given input using the variational autoencoders this time. So this is how our architecture is expected to look like. So we have encoders, encoder layers, we have sampling layer, and the decoder layer. And we will go through each of them during our hands-on example. So I'm gonna go ahead and start with the application. So do you have any questions so far?
So in the first figure, you mentioned, there were not this one, but there was one more in the introduction wherein you showed a figure of a person, and the next one, yes.
Yeah.
So here you showed the latent attributes like the hair color, glasses, and so on and so forth. Are these things specified, or are these part of the input, or like?
Oh,
So do you pass an image as well as all these features along with it?
it depends on what you want to do. So for the MNIST data set, what I'm going to do is I will let autoencoder to find their own features, but you can introduce some supervised learning elements into it. If you have the data about how much this guy is smiling, what is the skin code, sorry, tone, gender, those kind of features, then during the training, you can introduce those features as a physical guideline to your variational autoencoder.
Okay, so the latent attributes that you are showing is could as well be a part of the input data set.
Yes,
Okay.
but
Okay.
it doesn't need to be.
Okay.
Okay. This is a more sophisticated variational autoencoder. In fact, what many people are doing when they start talking about the distributions is they start talking also about the generative adversarial networks, because data generation is something that you don't want to do it blindly. You want to generate the data based on some attributes that you can predefine. So,
Okay.
like I said before, this is not a must, but it enables the training towards a better and more realistic looking face pictures, if we are specifically talking about the faces.
Okay.
Okay, let me find my. All right. So do you see my screen?
Yes.
Okay. So yeah, so what I'm going to do is I'm pretty much going to follow the same pattern that I follow for the autoencoders. However, this is going to be a little bit longer. So again, I'm going to import the MNIST data set. And also, let's load the data for them. So we have the training and testing data. think this is correct. And we have, so I'm not going to use a convolutional neural network. So, but it really doesn't matter. So I'm just going to use the densely connected networks. Hence, I need to reshape again the neurons. And I have like 60,000 of images for the training. And likewise, I have 10,000 images for the testing. And after I reshape, I need to normalize them as well. So typical normalization is because there are like 256 pixels, so I divide it by that number. And by default, if you remember, those were integers, so I have to cast them to float numbers. And let's do the same thing for test as well. Okay, now I can start the network. So first I have the inputs, and the input shape is going to be what? So the typical MNIST data set is 20 by 20, 28 by 28 dimensions, pixels. And then I have a hidden layer, which is the dense network here. And I'm gonna use the activation function as ReLU, which takes the inputs. Now, so let me back up a little bit here. So what I have here is I'm trying to create this sampling layer, and a sampling layer requires the means and standard deviations. So I have to define those two layers first, and then I'm going to define the sampling layer. So which is going to be, so you can use as many hidden neurons for the means and standard deviations, but 2 is usually enough. And I have also the standard deviation. That is also 2. So I have 2 layers connected to the hidden layer. And last step is going to be my custom layer, which is called lambda layer in this case. And it is going to sample it is going to be a distribution, and it will sample from a distribution that has this mean and that has this standard deviation. So in other words, the input to this layer is going to be standard deviation and that mean. So now, and the output we can define it as 2. We can have a larger shape, but usually it's a good practice to match the number of neurons that you, the number of neurons that you choose for the mean and standard deviation layers to match with the sampling layer. Okay. Now we have to define how to do the sampling Usually for variational autoencoder, sampling is done over the Gaussian distribution that is defined by mean and standard deviation that we are going to provide. So what I'm going to end up with is sampling. Yes, sampling. So I have this function is going to take like 2 arguments. And I have to be careful here because each sample may have a different batch size. So I'm going to like store those information to make sure what's going on. So that K is a special function reserved for backend operations of Keras. So I have to import that function. While I'm on it, actually, I didn't define the input layer, dense layer, and lambda layer, so I'm going to take care of that too. So I have lambda, input, and dense. This is going to be back and SK. Okay, now it's correct. All right, let's go back to our sampling function. So we have the batch size. So each matrix has each tensor has 2 dimensions here. So the first one is going to be the batch size, and the second one is going to be the dimension. Or we could simply also write it. So this is another feature. This is another function from backend. So we could also directly get the shape as the integer. Now, we are going to create the distribution using those 2 values, the mean and the standard deviation. So again, the backend has a feature to create a distribution, a normal distribution. And the shape is going to be the batch of the input and the dimension of the input, so that the dimensions of the samplings that we withdraw from our normal distribution is expected to match with the input to that layer, which is basically the batch and dimensions for the means and standard deviations. So our last step is going to be this is by itself a normal distribution. Each normal distribution has a mean, and it has a standard deviation, and we do this by e to the power of 0.5 times z standard deviation times f1. So this is like a standard way of defining a normal distribution that has z mean and z standard deviation. And this layer is going to provide the sampling data that is asked by the our sampling, well, it is asked by the sampling layer. So I don't know if it makes so far. So what we have here is, again, the input, the hidden layer, and the sampling layer, which takes the z mean and the z standard deviation And it uses these two values to create a distribution, a normal distribution, and it picks up some values from that normal distribution. So the reason why we are doing all these is because later we are going to use those distributions, this picked samples, to compute the divergence criteria. So this is basically our encoder plus sampling. And the next step is going to be like creating a model out of given input. Now, the next step is going to be creating the decoder. And for the decoder, let's see. So we can make it modular. We can assume that we have like latent input, which has the input shape of 2. And then what I'm going to do is like combine everything so that it becomes a single big model. So I'm doing this for the sake of modularity. Later, you can use the decoder part and encoder part separately to train the network or generate the data, or both at the same time. Okay, so we have the input. Now I have the dense hidden layer network for the decoder that is going to take the latent inputs. So dense. I can use the ReLU for this section. And finally, I'm going to get the output after that dense network. So just to show what's going on here. So we did the encoder part here and also the sampling part. Now I'm doing the decoder part. The decoder part has a hidden layer and it has an output layer. So I have the hidden layer here and I'm going to create the output layer. And that's going to be, I have 28 by 28 pixels. And because I want to use the binary cross entropy for the loss function, the activation is going to be sigmoid for the loss layer. Of course, this could be MSE as well, but let's be consistent with the first autoencoder example that we covered. And finally, let's create the decoder model, which takes the latent inputs and spits out the outputs. Let's combine everything. So combine encoder and decoder. So we have, hang on, there's one more thing. So yeah, let's combine everything. So I have the outputs, and the outputs is supposed to be so I can do both ways. Like I can either go this way, or I can create explicitly what outputs is going to be. So outputs is going to be decoder, which takes the encoder, which takes the input. But the latent feature is going to be only matching the sampling distribution layer, the lamp layer. And if you look at the Z, no, not the Z, the encoder has 3 outputs. So I have the mean, standard deviation, and the distribution layer. I only want to get the distribution layer for the streamlined process if I'm connecting decoder to the encoder in this case. And then the final step is just creating the entire model. I have the inputs, outputs. Let's run this so far and let's see if we have any problems. So I'm going to terminate these guys. Of course, we have to load the NumPy. So import NumPy. Yes, we have to also import the model. All right, I wonder what the error is.
Incompatible. I don't see it. Do you see it? Let's go step by step. Is it the final model that is creating the problem? No, not really. So it is how I'm putting everything inside one model. Okay, let me try this. I have already written some parts of it, so let's see. I don't think this is a problem, but let's see. So by the way, these are already, or it is going to be in the repository in the GitHub. So, and the one in the GitHub is working for sure, that I can assure you. All right, it's working now. I don't know what was wrong previously. You gave name equal to VAE here. Right?
Yeah, but that is the only difference, right?
In both the cases, yeah.
I can check that and let's see what's happening. So
I think you miss giving names to the encoder, decoder, and the VAE.
Oh yeah, it
so
made
that's
it. Yeah, this was a problem then. I forgot to give the names for it, and then this was complaining about it. So let's go with the losses. So I have two losses, like I said before. It's one of them is reconstruction error, and the other one is the k-loss error. So, and the reconstruction error is binary cross entropy. I think I need to define that here as well. So from Keras, also. Okay. So we have the binary cross entropy, which takes the input and output. So by default, reconstruction error, the binary cross entropy gives the mean error. Just to let you know, I'm going to do the same for the KL divergence. So the paper comes up with an equation. So I'm just going to plug that here, but it doesn't need to be like this. So for other types of divergence criteria. So let's see. To the power, is it? I'm not done yet, and I need to take the mean value of this. So it's going to be, actually we can write it like this, K mean. There's a little coefficient that is required for KL to work. And then the VAE loss is going to be the combination of those two, which is basically the reconstruction loss plus KL loss. So we need to add this loss to our network. And finally, we are going to compile everything. And it's going to give us an error, but still it's going to work without any problem. Not an error, but a warning. And you can use any optimizer. I'm just using the Adam here. Okay. Didn't I justify? Okay, here we go. All right, let's go. Now the last step is going to be, so this is going to take a lot of time. I'm not going to wait here to like get a proper result, but what I have is like, I can set the, just like I do with the autoencoders, I can set the input, the epochs, the batch sizes. Again, if I want to shuffle the data, because we are doing training and we want to generalize everything. And then we can also provide the validation data as well. We don't have to do that, so I'm just going to skip it for now. Epochs. All right, what else now? Batch size. It doesn't work in the first time ever, does it?
Never.
Oh yeah, of course.
I remember I had earlier a colleague. His name was Harman. He still joined ISIS again, and we worked on a problem together. And I made him a bet. We are doing like a pair programming, and I made him a bet that we are going to write like about 300 lines of code, some big function. And if it works the first time, I'm going to go and buy him a sandwich at Subway.
Yeah, actually, it's scary if it works the first time.
I didn't, but I bought the sandwich anyway.
Um, I still don't see the error, but what I have is the again the working version of it. It is I don't see what I'm doing specifically wrong right now. I'm guessing it is the
You can just
dimensions right
copy
now.
from the GitHub, I guess.
Okay, yeah, I can do that. Instead, I can use the one that is already done. Yeah, so if you go through this example, so what you are going to have, this is, I think, only for, was it 10? Maybe probably this was only for 10 epochs.
Yeah.
So the numbers, the reconstruction is not very successful. So 7 looks like a 9, 4 looks like a 9. Every other number looks like a 9 when you are not doing very well training. But if you increase the epoch numbers, so there is a possibility that you will get better match, but that is not guaranteed at all though. Sometimes, so that's the downside of the variational autoencoder, because now you are training against a distribution. You have to have a lot of data and you have to do a lot of training with that, a lot of data. And then if you were providing random input to your variational autoencoder, then you could create a set of numbers, like it is varying from 7 to 1 or 7 to 9 or 7 to 5. This is using the decoder part, and we are just giving arbitrary numbers to the decoder part to generate different numbers. And as you see, this is the problem with the autoencoder. So variational autoencoder, it is capable of generating intermediate values between 7 or 1 or 7 or 9. But when the network generates those kind of numbers, we cannot understand as a human what it is. And that may be sometimes not very useful. But imagine we are not talking about the numbers, but faces. We could actually utilize those variations in small amounts of features for different faces, like the skin tone by itself, right? A small change doesn't.
Probably that website that you showed, this person doesn't exist, uses something like this.
Yeah, it is. It is.
Okay.
Yes. So I'm going to rush through the generative auto for adversarial networks because we have like 8 minutes left. So, well, we know that already if we have the distributions that we can extract from the variational autoencoders, we can generate data. But like in the last 5 years, I think, people came up with a different way of generating data. It's actually called generative models. That is a new set of like networks that are that usually have 2 components. One of them is like generator, which generates the new examples, and the same network is also capable of classifying the examples as real or fake. Usually a generative adversarial network, or a GAN, is a 2-player game. And within that network, the generator tries to generate examples that can cheat the discriminator. And discriminator is trying to detect all those fake examples. And there's a constant battle between the generator and discriminator. And that battle is what improves the capabilities of generator as well as the discriminator. And the end goal usually for GANs is generating examples that cannot be detected by the discriminator. And discriminator's end goal is detecting every fake example, but that is usually not possible. So the reason why it is called adversarial network is because we are trying to cheat the generator model or generative model here. We are trying to create a system that can cheat the discriminator model. And in order to do that, we have to create adversarial examples constantly that is withdrawn from a sample that is constantly updated through the backdrop mechanism that neural networks are providing for the training. So what happens is like during the training of a GAN is we provide a random network to a generative model during the feed-forward phase. And we also augment some real examples with the generated examples. So during the supervised learning phase, for the discriminator model knows which example is fake, which example is real, and it tries to update its weights to address that classification properly. And then also based on the success of the discrimination, the generator model updates the latent features for its distributions. And the reason is because it wants to create examples or generate examples that cannot be properly discriminated by the discriminator model. And this goes on a cycle like this. So at every step, generator model creates examples that is supposed to cheat discriminator model, and discriminator model generates results and notifies the generator model that says like, your examples are not good enough. You need to update your latent feature space to address what is fake and what is real. The problem is, so many people are using adversarial networks and generative adversarial networks to train the networks against attacks. Because if you know what is an attack, supposedly you can defend against it properly as well. The problem is, while that is theoretically true, it is in practice not correct. So there is always a discriminator model that can fail to detect what is fake and what is real compared to a generator model that is supposed to create fake examples. So therefore, if you are trying to protect your network against adversarial attacks, GANs are not always the best choice. But what it is best for is you can create domain-specific examples, and if you are trying to create another model using the data that you don't have yet, so you can create and augment new data using the generator model. And then you can train your new network based on that generator model generated examples. So just to give an idea what the GANs can do is like there are two images. These are both fake, but they are very realistic to the human eyes. If you look very carefully, maybe you can see some little issues, but if I was told that these are real, I would believe so. Most probably, their discriminator, which trained these generators, supposedly it can detect these images as fake. But if I created my own GAN, and if I created my own faces with a new method, it is probable that the discriminator is not going to be able to classify the images that I create as a fake. So that's the problem with the GANs. The discriminator is not very efficient against other examples. They are efficient against themselves, though, so that is good. Usually GANs are, again, used for attacks, or to create new social issues. So there's the defect that is creating a lot of issues that you can put other people's faces on the videos, which I find it crazy. You can also clone the voices of real people. So for example, I can talk and you have all of my talk data right now. You could train a network which can convert your voice into my voice. So, and you can call someone and imitate me to access to private information. So that is the end of it. I again put the references for generating the variational autoencoders, as well as the generative adversarial networks. I didn't cover the code for the general GANs because it is even more complicated compared to VAs. It's really hard to create that. It's not that easy, but still it is possible if you look at the code pieces that I attached here. So I'm done. Do you have any questions? This, I admit that this is not very in-depth, but it is trying to explain what is going on superficially and how you can create your first variational autoencoder.
Well, that's pretty good actually, and right on time.
Yeah. Do you have any, like, what are the use cases of the two, like variational autoencoder or GAN? Like, what are some of the use cases apart from these deep fakes and other, like, is it specific to the images or can you use it for other?
I didn't use any other example other than GANs for now. And it is also the same for the variational autoencoders. What people usually doing is there is this concept called domain adaptation. One portion of domain adaptation. So domain adaptation means, so you train a network for a known input that has a certain distribution, but then when you test it with an input that has a different distribution, your network may not behave very well. So one idea is, can you extract latent distribution of the given input or for any input that is unknown to you? And can you shift the distribution internally from, like, you train the network for the known distribution. So can you update the means and the standard deviations to match the latent distribution for the unknown input data? So that is called adaptation. So that is an idea. And I don't see any other applications other than like those fun, I call it fun applications. I don't see they have like 100% scientific contributions.
Yeah, I mean, I was wondering, like, why would one use some of these rather than using like neural network or other regression or other models? Why would somebody use a GAN or a variational autoencoder? And what use cases one would find these useful?
Usually, overall idea is data augmentation.
Okay.
If you have limited data, you can generate more data. That can be called as a genuine domain data. They are fake, but they are well enough for you to do your job. So,
Okay.
for example, these faces. you know they are fake, but you can consider them as a real examples.
Right,
If you
right.
are trying to, for example, detect human activity with respect to faces, or if you are trying to um,
Right, I
predict
think.
the age of the people, for example.
Mhm. Yeah, I think augmentation would be a very good use case as well.
Yeah. I try to use the variational autoencoder for my own research using like damage detection. I didn't have good success. So I guess it doesn't apply to every case. And I think the problem with me was the Kullback-Leibniz divergence criteria is for some certain applications, it may not the best divergence criteria. An alternative criteria is, which I tried to use, was maximum mean discrepancy.
So I think it is possible that with this new data that you generate, it depends on how you are going to use it, the success of it. So if you use it in the similar way in which you were using the earlier smaller data set, then obviously this is fake data that you generated and it's gonna dilute the purpose. But if you are using for other things, like in this case, the images, you mentioned that you generate these fake images, but use it for other kinds of analysis, like, trying to extract features or try to guess the age of the person or something like that. Another example could be like in the communication networks. So if you are going to generate different type of traffic patterns, and then use other that generated data set for other kinds of analysis, like you are trying to train your or devise or find strategies which are better against defending the communication network. So you use that fake data set, which is not fake but still very similar, but using it totally different purpose. So I think the purpose that you use it for may actually make a big difference in how useful they are.
Yeah, I agree. So
Okay.
yeah,
I think
I don't have.
I think for the application of variational autoencoder, I remember actually. Oh, sorry, can you hear me?
Yeah, we can hear you.
Oh, yeah, sure. Okay, I think Fei Yang actually has a work, published a paper in ICCPS using the VAE to do the anomaly detection. And his application scenario is, train a variational autoencoder on the autonomous driving scene camera, and use that data to do the image scene reconstruction using the variational autoencoder, and try to do the anomaly detection on it to detect whether this current camera input is coming from the same distribution.
Yeah, I remember that.
Okay.
Yeah, so in general, autoencoders can be used for anomaly detection. And like I said, I didn't have a good success with the variational autoencoder, but your mileage may vary. So
Yeah.
um,
Okay.
so I'm also I don't see for the guns, I don't see anything other than images, but I know that for a fact you can um, use it for voice cloning. There is actually one application. You can create paintings. Like you can give the input and it creates a painted version of it.
Okay.
And I remember I mean, for the generative model like this, I think there's another application. I mean, using these models for the data generation to in order to preserve to generate a data set without leaking the original information. I mean, to do some privacy preservation for the original data. I think there's Professor Brad Malling's group. Actually, they are doing some of the work using the GAN to generate medical data for patients to generate new data sets without leaking the original patient's information.
So are you saying that if I have enough generated data, I could supposedly create the original images that created the generative models? I mean, that is kind of the posterior probability problem, which is intractable.
I'm not
But
quite sure about their details, but they just told me, just told me it's something like, I mean, to generate a new medical scenario data set, but and meanwhile preserve the privacy of the original patient's data, something like this.
Okay. I think maybe, that's not how I think that. It's just they have data, they want to provide the data to other people, and they want to protect the patient information. So the best way to do it is generate new data out of the protected information.
Yeah, I guess that's what they are doing.
I think if anybody else have any questions, if not, I think thank you very much, Ali, for sharing this knowledge. I think it was useful.
I hope so.
Yeah.
Thank you.
Yes, thank you for your lecture.
Thank you.
Thank you very much, guys.
Have a good day, everyone.
You too.
Okay, bye.